session chair. My name is Jasper Snook. This is track 1, session 2, I believe, on reinforcement learning and neuroscience. We're going to start off with a set of spotlights. So the next speaker, please make your way up here. And like I said before, please sit down. We've been told it's a fire code hazard or something. If you're standing up, so find a seat as soon as you can, please. Okay, so without further adu, the first talk is going to be Breaking the Curse of Horizon, Infinite Horizon Off-Policy Estimation by Qiang Liu.
Thank you very much. This is a joint work with Lihong Li and Danny Zhou from Google and my student Ziyang from UT Austin. So this work is about off-policy evaluation. So the problem is to estimate the total expected reward of some policy pi, given only what's called off-policy, meaning that the off-policy data that is drawn from another different policy pi 0. Right. So this problem is a very important problem, tremendously important in many different areas in which we need to, it's very expensive to evaluate new policies in areas like medical diagnosis, robotics, and advertisement. So one of the key challenge, which we call curse of horizon, is that when the length of the horizon length of the problem increases, the problem tends to be more difficult and existing algorithm tends to break down. So here's an example. Let's say if we use the typical importance sampling, we will end up with an importance weight that is a product along the whole trajectory, so that the variance of the importance weights actually grow exponentially with the trajectory length. And we even get infinite variance when we have infinite horizon problem. So the goal of this work is to address this curse of horizon in a principled way. So our key idea is actually very simple. So instead of applying the importance sampling on the whole trajectory like the typical algorithm does, we apply importance sampling on a stationary visitation distribution of the S and A pairs. In this way, we just get rid of the dependency, at least the explicit dependency over the trajectory length, and get much lower variance than the standard importance sampling. So, of course, one of the key challenges is to estimate this new density ratio. And we did this by designing a new minimax objective function. So it works a bit like generative adversarial methods, but we can actually kernelize one of the steps, so we'll get a standard minimization algorithm. We show that this algorithm has a very nice theoretical guarantees. So we did a bunch of experiments. So this is an example when we use reinforcement learning to control traffic lights. And we find our method outperforms existing methods. Thank you very much. Welcome to my poster.
Okay, so the next talk is called Graph Convolutional Policy Network for Goal-Directed Molecular Graph Generation by Jiaxun Yu. I think I did that terribly, but here he is.
Hi, I'm Jiaxun from Stanford University. Today I'm going to present our work about goal-directed molecular graph generation. Our work is motivated by the task of drug discovery. Specifically, we care about the task about generating novel molecule structures that have high value of a given chemical property while being chemically valid and realistic looking. Here, the 3 key requirements are valid, realistic, and high scores. I will mention them throughout the talk. Based on the motivation, we propose the following goal-directed graph generation problem. Specifically, we want to generate molecule structures that can optimize some given objectives. For example, drug likeness for molecule graphs. Note that this kind of objective is not differentiable with regard to input. Secondly, we want the generated graphs to obey some underlying rules. For example, for molecule graphs, it should obey the chemical valency rules. Finally, we want the model to learn from examples in order to incorporate prior knowledge from given data sets. There are two lines of existing approaches for the task. The first will use string representations plus reinforcement learning. A molecule can be represented as a string like this, which is called the SMILE strings. However, this kind of approach is very likely to generate invalid strings, because even one wrong character can make the entire string invalid. The second line of work will first use variational autoencoder to learn a vector representation for graphs. And then it will conduct Bayesian optimization in the latent space and finally decode the molecule structure. This kind of approach is highly dependent on the quality of the learned latent space, and it requires hand-coded rules in the design of the decoders. In this work, we propose the approach that uses graph representations plus reinforcement learning to solve the task. There are three highlights in our model. The first is that we propose to use graphs to represent molecules. This enables validity check in each state transition, which ensures that all generating molecules to be valid. The second component is that we use reinforcement learning to directly optimize the property scores through the design of intermediate and final rewards. Thirdly, we use adversarial training in order to incorporate prior knowledge from a given molecule graph data set. The key component of our approach is the Graph Convolutional Policy Network, or GCPN. The GCPN operates on states and produces a policy, and specifically, a state is defined as a partially generated graph. GCPN will first compute node embeddings for all the nodes using graph convolutional neural network. And then it will predict the next potential edge, edge type, and stop token using multi-layer perceptron. Based on the policy, the agent will sample an action, and finally, the environment will conduct validity check and update the state. The GCPN is optimized using PPO policy gradient methods. In the experiment, we consider two types of tasks. The first is to generate graphs from scratch. We show our model can achieve 60% higher probability scores compared with data of our other methods. And we can have molecules with 100% validity. The second line of approach, we use GCPN to modify existing graphs to achieve higher properties. And we show that our model can achieve over 180 higher percent of scores improvement. We also saw three lines of visualizations, where the two columns shows the molecules generated from scratch based on two different objectives. And the third column shows our model, how our model modifies existing molecules to achieve higher properties. Come to poster number 140 for more results. Thank you.
Okay, so our next talk will be Memory Augmented Policy Optimization, MAPO, for program synthesis and semantic parsing. And Chen Liang will be presenting.
Hi, everyone. I'm Chen from Google Brain. I will present MAPO, or Memory Augmented Policy Optimization for Program Synthesis and Semantic Parsing. This is joint work with Mohammed, Jonathan, Kwok, and Ni. So we consider the task of program synthesis from natural language, also known as semantic parsing, where you have a natural language question and a database table, and we want to train a model to learn to generate a program that compute the correct answer. For example, given the question, how many more passengers flew to Los Angeles than to Saskatoon? The program needs to first filter out the two rows corresponding to the two cities, and then compute the difference as a passengers column and return that as a final answer. So annotating the true program for each question can be expensive and time-consuming because it requires a lot of human expertise. So instead, we want to treat the programs as latent and only learn from the final reward whether the program returns the right answer or not. The reward can be very sparse because in the exponentially large program space, there are only a few programs that can return the right answer. So sadly, we know that whenever somebody asks you if RL works currently, most of the times it doesn't. So despite all of the successes, it's still challenging to apply RL for real-world applications. So for example, policy gradient is one of the mostly commonly used RL methods. So in the simplest form, it contains an actor that keeps generating samples from the current policy. So in our case, the samples means programs. And then they will be sent to the learner to estimate the gradient and use that to update the policy. So the good thing is the gradient estimate is unbiased. So given enough time, you will reach an optimal solution. But because you're only estimating the gradient from a few on-policy samples, the variance is high, so the training is slow. So on the other hand, imitation learning tries to train the learner from external demonstrations using, for example, maximum likelihood training. So the training is much faster, but because you're not directly optimizing the expected return, the final solution can be suboptimal. And also, it requires human supervision, which is usually hard to get. So Maple combines the advantages of the two above methods by first saving a bunch of high-reward samples from the actor to a memory buffer, and then mix samples from inside and outside memory to generate, to send to the learner to estimate an unbiased gradient estimate with low variance. So why is the variance lower? So the gradient estimate is computed as expectation over the whole program space, which can be exponentially large. If we just use sampling to estimate the expectation, there's a lot of variance. So instead, in Maple, we divide this into two partitions, the programs inside memory and programs outside memory. When the number of programs inside the memory are small, we can enumerate them and only sample from the outside, which is a smaller subspace, so the variance will be reduced. And even when we are also sampling from inside the memory, this can be viewed as stratified sampling, and the variance reduction usually still holds. So in the equation form, it looks like this. So we decompose the expected return objective into a weighted sum of two terms. So the first term is an expectation inside the memory buffer B, and the other one is expectation outside the memory buffer B. So you can see our posters or paper for more details. So we use two challenging semantic parsing benchmark for evaluation. On wiki table questions, Maple is the first RL-based method that achieved state-of-the-art and is significantly better than previous state-of-the-art. On wiki SQL, although most of the state-of-the-art methods are using ground truth programs as strong supervision, surprisingly, Maple, although using only final answer as weak supervision, achieved a comparable result. So comparing to other baselines, Maple converges slower than iterative maximum likelihood estimation, but reaches a better solution, while reinforced doesn't make much progress at all. So in summary, we present Maple as an efficient policy optimization method for learning to generate sequences from sparse rewards, which can be viewed as a deterministic environment. And we also believe Maple as a generic variance reduction technique can be applicable to a range of other problems as well. So for more details, please check out our paper or open source code or come to our posters at 137. Thank you.
Okay, our next talk will be on meta-reinforcement learning of structured exploration strategies by Abhishek Gupta.
Hi, everyone. My name is Abhishek, and I'm here to talk about meta-reinforcement learning of structured exploration strategies. To start off, let's compare human exploration with robot exploration. Let's say we have a task which involves putting a shape into a shape sorting cube as shown here. When a robot learns how to do this task, the exploration looks something like this. It's quite random and not very efficient in the way that it explores. On the other hand, when a child is learning how to do the same thing, the child is able to pick up the block and is much more directed and coherent in what it's doing. So why exactly is the human exploration strategy so much better than the robot one? One hypothesis is that the human is able to better leverage their prior experience in order to guide their exploration on new tasks. Can we do the same for our robots? So let's consider a scenario where a robot has prior experience on a number of different tasks, each of which involves picking up a different object, as shown here. Now, when you have a new task where the goal is to pick up some unknown object, a good exploration strategy could be to try picking up different objects rather than just wave your arm about in the air. So we want to be able to use our prior experience to firstly inform more effective exploration strategies for new tasks, and secondly, be able to quickly adapt to these tasks. Right. So in order to do this, we introduce an algorithm which we call model-agnostic exploration with structured noise, or MASON, which has two key insights. The first insight is that you want to explore in the space of random but structured behaviors. While you still want randomness in your exploration, you want it to be along the axes of more directed and coherent things like picking up different objects. And secondly, you want to be able to quickly adapt to new tasks. So you can explicitly train your policy to enable this kind of quick adaptation. So let's say you have a scenario with a number of different objects. A good exploration strategy might try to pick up different objects. And on receiving some reward for grasping the red object, you should have the policy quickly adapt to consistently pick up the red object only. So what exactly do we mean by structured exploration? Well, in typical methods, you introduce stochasticity by sampling actions independently at every single time step. Now, this makes it very difficult to have coherent exploration behaviors such as picking up different objects. In structured exploration, the agent's going to pick an intention at the start of every episode and stay with that intention through the entire episode. At the next episode, the agent picks a different intention and sticks with that intention through that entire episode. So the exploration is happening at the level of episodes across different intentions rather than at the per time step level. And this makes it much easier for us to do more coherent explorations, such as picking up different objects. So the policy needs some sort of mechanism to decide how it wants to explore at a given episode and stick with that decision through the entire episode. In order to do this, we augment the policy with the latent random variable z, which is sampled from a latent distribution q omega. Now, at the start of every episode, the policy samples z from the latent distribution and then keeps it consistent through the entire episode, thereby deciding how to explore that episode. Now, we want that different z's represent different meaningful behaviors, such as picking up different objects. And learning in this scenario then corresponds to using your prior experience in order to train the latent condition policy to effectively use your latent space to explore in the space of meaningful behaviors while discarding behaviors that are less likely to be useful. Now, we don't just want our policy to be good at exploration, we also want it to be able to adapt quickly to new tasks. So let's say sampling from your prior gives you exploration that looks like this. When you get some reward for picking up the red object, you want to be able to move your sampling distribution in latent space such that it's only picking up the red object. Now, we also want this to happen for the blue object, the green object, and many different tasks, so we can explicitly meta-train our latent condition policy to enable fast adaptation. In order to do this, we introduce an algorithm based on the framework of model-agnostic meta-learning, combining the benefits of fast adaptation with structured exploration. And we invite you to come to our poster for more details on this. So, to some results. The first task we considered was using a robotic block pusher to push different blocks towards the goal. And we see that random exploration is not very effective. It doesn't actually touch any of the blocks of interest. On the other hand, we see that Mason is much more coherent in its exploration strategy. It's able to explore in the space of pushing different blocks towards the goal and is much more likely to experience reward. It's also seen from the trajectories of the pusher as shown here. The second task we consider is exploration using a quadrupedal robot which has to navigate to different points in the plane. So we see that random exploration is not really making much progress and simply flailing around. On the other hand, exploration with Mason is much more coherent. It's exploring the space of walking to different points in the 2D plane. So it's much better and likely to get better reward. We also see that we're able to adapt very quickly to new tasks and achieve higher asymptotic performance than methods that use structured exploration without fast adaptation, methods that use prior meta-learning algorithms, and methods that simply learn from scratch. We invite you to come to our poster for more details, and I want to thank all my collaborators. Thanks.
Okay, so Okay, so we're going to have our first longer oral of the session on policy optimization via importance sampling by Matteo Papini.
Hi, I'm Matteo from Politecnico di Milano, and this is a joint work with Alberto, Francesco, and Marcello. I'm here to tell you about policy optimization via importance sampling, a novel policy search algorithm that uses off-policy evaluations in order to make the best use of the trajectories it collects. Our goal in reinforcement learning is always to find the optimal policy. A policy pi is a possibly stochastic mapping from states of the environment to actions of an agent. And each policy induces a specific distribution over trajectories that are sequences of states, actions, and rewards. The optimal policy is the one maximizing the sum of rewards under this induced distribution. In policy search, we typically fix a class of parametric policies and search for the optimal parameter within this space. Now, compared to a classical optimization problem, we have some additional challenges in RL. First of all, we have to collect our data, and this can be very expensive because it requires to interact with the environment. But most importantly, each policy induces a different distribution over this data. And this means that to properly evaluate a policy, we need data from that very policy. So to perform our search, we need to evaluate candidate solution, and to do so, we either have to collect plenty of data with a lot of different policies, or to perform some sort of counterfactual reasoning, which is known as off-policy learning in this case. The key intuition here is that with data collected with a policy, you can evaluate quite well policies that are similar, but you cannot say much about very different ones. Now, policy gradient methods, such as reinforce and PGPE, use the data collected with the policy to evaluate just the policy itself. Then find a direction of improvement, perform a small policy update, obtain a new policy, collect data with it, and so on. These can become very sample inefficient. We would like to use data collected with this policy also to evaluate other ones, to save some data. For instance, constrained optimization methods, such as TRPO, allow to evaluate policies that are within a reasonable neighborhood of the one used to collect the data. A more direct approach is to optimize a surrogate function that explicitly penalizes policies that are too different. This is the approach followed by PPO and now also by our algorithm. So our algorithm is policy optimization via importance sampling, or PUA. It's pronounced PUA, which is the Italian word for polka dots. Our surrogate function is a statistical lower bound on the performance estimated with importance sampling. The bound is a typical Chebyshev-like bound with a sample mean component minus a variance component. We studied different bounds from the literature, but this turned out to be the most appropriate because of the heavy tail nature of the importance weights. Let's look into this. So we have data from a behavioral distribution. Here is Q, which can be our current policy. We want to evaluate a function, performance, in expectation under a different distribution P. That can be any candidate policy we care about. Now, the importance sampling estimator is just a weighted Monte Carlo estimator, where the weights are probability ratios. This is an unbiased estimator, but these weights can introduce a very large variance, which grows exponentially with the distance between the two distributions. By knowing the range of our function, we can bound the variance of the estimator by this exponentiated Rayleigh divergence, which is also the second moment of the importance weights. Now, the real problem with this estimator is that it can badly misevaluate distributions that are far from the one that generated the data, the behavioral. But with our bound on the variance, by applying Cantelli inequality, we are able to lower bound the real performance of any candidate solutions by subtracting from our estimator a penalization term that accounts for the variance. This penalization contains the exponentiated divergence between the distribution, so as intuition may suggest, it grows larger and larger as the distribution grows different. This is a general bound. We can apply it to different policy search paradigms. In the action-based paradigm, we optimize the parameters of a stochastic policy. And here, stochasticity is fundamental because it allows to explore new actions. Instead, in the parameter-based paradigm, we optimize the parameters of a hyperpolicy, that is a distribution over the policy parameters. Here, the policy itself can be also deterministic, since exploration is ensured by the stochasticity of the hyperpolicy. If we apply PUA to the action-based paradigm, we have to compare distributions over trajectories, and these, in general, are intractable. Although we can easily compute the importance weights as products of policy ratios, the Rényi divergence between the distributions must be estimated from data. Moreover, this penalization is amplified by the length of the trajectories, that is the horizon of our task. Instead, in the parameter-based version, we simply have to compare hyperpolicies that are distributions over policy parameters. In this case, the Rényi divergence can be computed exactly. Moreover, the penalization is not amplified by the task horizon, but by the number of policy parameters. Now, let's see the algorithm in action. Here we have performance, that is the sum of rewards, and we want to find the policy parameter theta that maximizes this performance, capital J. We start from some initial policy. We collect trajectories with it. Now, with this data, we have uncertainty about other solutions, and it grows exponentially with the distance from the behavioral. So we turn to our bound, which accounts for this uncertainty. We optimize the bound offline, which means we can perform several steps of optimization with the same batch of data. Now we have our new policy. It becomes the new behavioral, so we collect new trajectories with it. And now you see that the uncertainty landscape has changed because we are in a new behavioral. In this version of the algorithm, we also forget about what we have seen before, but more on this later. Now we can go back offline, optimize our bound again, and so on until convergence. In practice, we can employ additional techniques, such as self-normalized importance weights to reduce the variance of our estimator at the price of a small bias. We can use this concept of effective sample size to estimate the Rényi divergence more easily. And we can use natural gradient and line search to improve the offline optimization. Let's have a look at some empirical results now. Here you have learning curves. Remember that since we are maximizing reward, higher is better. So here we have the performance against the total number of trajectories that have been collected and which are organized in batches of 100 trajectories. So to make the comparison fair, we optimized the hyperparameters of all the involved algorithms, and we used 20 different random seeds. We compare with the state-of-the-art algorithms, TRPO and PPO, that you can see here. First of all, we learn linear policies, and so shallow policies with a limited number of parameters. Here, action-based PUA, which is the blue curve, performs better than these state-of-the-art algorithms on some tasks and comparably in other tasks. These tasks we are testing on are classical continuous control benchmark tasks. But here, you can see that the parameter-based PUA is visibly faster than its counterparts. Now, in tasks where exploration is fundamental, the gap between the two flavors of PUA becomes even wider. However, there are some tasks, like this inverted pendulum, where both versions of PUA performs quite poorly. This is a task with a very sparse reward, and we think that the current issue is that being trajectory-based, PUA is not able to properly value good actions within overall bad trajectories. We also learn deep neural policies. Here we report results from a popular benchmarking paper and our results. You can see that action-based PUA still performs comparably with TRPO, while parameter-based PUA here struggles. And this is because, as mentioned, the high number of policy parameters exaggerates the penalization term and so makes the algorithm over-conservative. To conclude, we have provided a novel statistical lower bound for off-policy evaluation. We have applied it to both the action-based policy search paradigm and the parameter-based paradigm. I think the main take-home message here is that with a principled approach to off-policy learning, you can do much more than just using your trajectories to compute a gradient and then throw them away. In the future, we would like to solve this problem of valuing good actions within bad trajectories by using per-decision importance sampling. And we would like also to reuse past data by using multiple importance sampling. Please visit our poster, number 109, upstairs, and you can play with our code. We have provided also a Docker file, so within minutes you can have it up and running. Thank you.
Great, so we have a couple minutes for questions. You'll see there's some microphones in the aisles. So if you have a question, please come up and ask away. Make it concise. If not, so I have a question. In the paper, you showed that there was this neat property of the Renyi divergence being expressed in terms of the Fisher information. I was wondering if you thought about using any of the recent approximations to the Fisher for kind of computing the Renyi divergence in a more scalable way.
Yeah, this is a very interesting question. So, yes, there is this relationship between the Renyi divergence and the Fisher, which is also useful for natural gradient optimization. Unfortunately, it is very difficult to compute this Fisher matrix in the action-based case, so we used it for the parameter-based case where it can be computed exactly, for instance, for Gaussian policies. I think doing some approximation of this could also help in the other paradigm with the action-based one.
Great. Okay, thank you very much. Oh, yeah, sure. Okay, so we're going to have our next set of spotlights now. Kicking it off with Won Seok Jeon. Is that close enough? Okay. A Bayesian approach to generative adversarial imitation learning.
Hi, I'm Won Seok Jeon at KAIST, and this is a joint work with Seok-in Seo and Ki-young Kim at KAIST and Prowler. Imitation learning is a sequential decision-making problem that can be characterized by Markov decision process without cost and a policy pi. Instead of using cost function, we usually assume there exists an expert or a set of expert demonstrations in imitation learning, and the goal of imitation learning is to find out the policy pi that mimics expert's policy as well as possible. The generative adversarial imitation learning, or GAIL in short, is an imitation learning algorithm that utilizes GANs for imitation. In GAIL, we first sample trajectories by using agent policy and expert policy, and then train discriminator that classifies whether state action pairs comes from expert or the agent. And then we run the reinforcement learning by regarding the discriminator as a cost function. The problem is Gale requires model-free reinforcement learning inner loops, which implies the environmental simulation is required. So we can naturally think about the sample efficiency issue of Gale and applying it to the task where obtaining samples is quite costly, for example, physical robots in a real world. So our motivation to solve this issue is to make refined cost function by training discriminator with Bayesian classification. So for Bayesian classification, we first look Gale in a Bayesian framework described as follows. We first consider the trajectory, which is a sequence of state action pairs, and it can be easily shown that a sequence satisfies a Markov property. So if we denote state action pair as a random variable z, the trajectory can be described as a graphical model below. In imitation learning, there are two policies. One is the agent policy pi theta, which is parameterized by theta, and the other is expert's policy pi e that the agent wants to mimic. Because each policy generates its own trajectory independently, so we can think about two separated graphical models below. So the remaining thing is how to add the discriminator in graphical model. And in the Bayesian approach, we usually consider the role of discriminator as the probability that models whether state action pairs comes from the expert or the agent. Also, regarding the probability, we can also consider the random variable O, which becomes 1 if state action pairs comes from the expert and becomes 0 otherwise. So by adding the random variables O's and the discriminator parameter phi on top of the trajectories, we can fully describe the probabilistic nature of Gale as shown in the figure. After describing the probabilistic model, we consider the posterior distributions to update the discriminator parameter and the policy parameter. The first posterior is used to update the discriminator parameter, which is conditioned on the probabilistic event that describes perfect trajectory discrimination. And the second posterior is used to update the policy parameter, which is conditioned on preventing perfect discrimination. By considering two kinds of posteriors, we can say that Gale uses maximum likelihood estimation for both policy and discriminator updates. Compared to Gale, our algorithm Bayesian Gale, or BGale in short, uses posterior predictive cost function and use the cost for reinforcement learning similar to Gale. In the end of our work, we check the performance, and our algorithm is shown to be much more sample efficient compared to Gale in 5 Mujoko tasks. For more information, please come to our poster session. Thank you.
Okay, so our next speaker will be Vichir Pong, and he will tell us about visual reinforcement learning with imagined goals.
My name is Vichi Pong, and this is work with my colleagues at Berkeley, Ashvin Nair, Murtaza Dalal, Sugar Ball, Stephen Lin, and Sergey Levin. What would it take to develop an autonomous learning system? For example, if we took this robot, put it in a room, and left it by itself, how could we enable it to autonomously explore the environment and develop useful skills, such as setting your dinner table or rearranging your furniture? Reinforcement learning seems like a promising approach, but if we put a reinforcement learning agent in a room and gave it no supervision, it wouldn't do anything. It would just wait for a reward. Without a reward, it has no incentive to explore the environment and learn useful skills, such as rearranging your furniture. However, we know that it's possible for agents to autonomously explore the environments and learn useful skills. For example, consider this autonomous agent. This baby isn't given any external reward, but it's clear that he's given himself a goal of reaching for this red toy. Through trial and error, it eventually learns to do this. By giving himself goals and practicing to reach them autonomously, he develops useful locomotion and manipulation skills. I should stress that this is doing more than just exploration. Yes, he's exploring the state space, but he's also learning useful skills that he can reuse for the rest of his life. How can we enable reinforcement learning agents to also autonomously develop skills? Today, I'll be talking about reinforcement learning with imagined goals. It's a method that enables autonomous learning by allowing an agent to autonomously set goals for itself and practice reaching them. It works directly from vision without access to any ground truth state information. And it's sample efficient enough to work on real-world robot tasks. Here's how it works. You put an agent in an environment. Its input are raw sensory observation, like an image of the table on the left, shown as X. As it interacts with the environment, it learns a latent variable representation of the world. This means that it maps high-dimensional image observations X into a low-dimensional latent representation Z, which it uses as its state representation. To allow our agent to set goals for itself, we actually use a generative latent variable model, which in our case is a variational autoencoder. We can use this generative model to sample new latent variables, which we then interpret as goals in this latent space. We then use reinforcement learning to train a goal condition policy to reach these latent goals. For our reward function, we use we use distance in the latent space. The nice thing about this reward function is that it's effectively learned automatically as our agent learns this latent variable mapping. This means that all of this learning can happen autonomously without any human supervision. Once this goal condition policy is learned, we can use it to do useful things. In particular, you can provide it a goal observation. For example, you can give it an image of what you want the dinner room table to look like. We then use the same encoder to embed this high-dimensional image X, shown in the top left, into our low-dimensional latent representation to get a goal ZG. We then give this to our policy. Because it's practice already reaching so many different goals, this will hopefully look like just another goal that it knows how to reach. We first tested our method on a variety of simulated environments, all of which work directly from vision. On the right, you can see one of these environments, which consists of a red robot arm in front of a blue and green puck. In the top left, you see what the agent sees. We see that by setting goals for itself and practicing to reach them, coherent behavior emerges. You might wonder what these goals correspond to, so we can actually use a trained decoder to visualize these goals, shown in the bottom left. And we see that these goals tend to correspond to pushing the object to given locations. As before, a human can specify a goal by giving a goal image shown in the top left, or bottom left. Again, we encode this image into our latent space and give it to our agent. And here we see that because the agent has practiced reaching so many goals, it already knows how to reach this human-specified goal. We also test our method on a variety of simulated environments. On the left, you see an agent has learned how to open a door to a target angle. And on the right, you see the agent has learned how to pick up an object and move it to a target location, all from vision. Lastly, we tested our method on a variety on two real-world robot tasks. On the left, we train a robot to reach a target position. And on the right, the agent learns how to push an object to a given location. Because our method works directly from vision, we don't need to buy additional sensors or buy object detectors. We just turn on the camera and let the robot learn autonomously. This is also really sample efficient, taking only 2.5 hours for the pushing task and even less for the real robot for the reaching task. We're really happy with these numbers, given that, again, this works directly from vision. We still have a ways to go before these robots can do your chores, but we think this is a good step towards developing agents that can autonomously acquire useful behaviors. If you want to play around with the environments or use the algorithm, they're publicly available here. And if you want to know more details, come find us at our poster tonight, 141. Thank you.
Okay, our next speaker will be Ian Osband, and he will tell us about randomized prior functions for deep reinforcement learning.
Hello, everyone. I'm Ian, and I'm here to talk about our paper, Randomized Prior Functions with Deep Reinforcement Learning. This is joint work with John Aslanides and Albin Kassira. So we're in the reinforcement learning setting here. And in particular, we think about this as combining supervised learning, for which the important thing is, making sense of data. But you also have partial feedback. So that has elements of a bandit problem. And you also have delayed consequences. Okay? And so this is sequential decision-making under uncertainty. And I guess I want to highlight there are three things that we know that we need, three key building blocks. So we need to be able to generalize, make sense of our data. We need to be able to handle the exploration versus exploitation trade-off. We need to get the right data. And we need to be able to do credit assignment. Now, at the moment, if you pick any two of those, I think we have methods in the field that are pretty good. But if you want to combine all three in a practical algorithm, in reasonable amount of compute, I think that we're stuck. And I guess in particular, one of the bottlenecks is that if you want to be able to explore with generalization and long-term credit assignment, you need to know what you don't know. And you need to have effective measures for uncertainty in deep RL. And that's what this paper's about. Now, I guess before I get into our method, I'm going to take the risk of outlining a few of the other popular methods and maybe present a hint that there could be shortcomings in them. And I guess dropout sampling. You know, everyone knows, I guess, the meme, or I guess that if you take a dropout sample, well, that's a posterior sample. But I guess there are some issues, is that if you pick a fixed dropout rate, it doesn't concentrate with the data. And if you do concrete, it might not concentrate at the right rate. Variational inference, you know, apply VI to Bellman error. A lot of papers do this. But there's an issue that if you look at the Bellman error on just a single time step, that might not propagate your uncertainty over multiple time steps in the right way, if you don't take care of the correlations. Distributional RL, you know, oh, we're going to model the Q value as a distribution instead of a point estimate. But you know, it's important that this distribution is not really the same thing as your uncertainty. Distribution over noise is not the same as distribution over your uncertainty. We have count-based density models. You know, you add a bonus, intrinsic motivation based on how often you've been to a state. But there's a problem that the density model might not have anything to do with the task at hand. And in general, when you have generalization, saying, have I been to this state, is not the same as answering the question of, do I know what to do in this state? So now on to a final one, something I've been working on myself. You know, I say, hey, we don't know how to do this. We're going to try bootstrapping from statistics. Train models with bootstrapping. Classical statistic procedure, great guarantees, whatever. But this is a clear failure, because if all your data is zero, very sparse rewards, why wouldn't you just predict zero? You have no prior mechanism, okay? If you've never seen a reward, why would you explore? Now, clearly, I don't have time to go through all of these points in detail, but hopefully they're evocative enough that, you know, someone will get interested and say, hey, Ian, you've got it wrong. So come to me and we'll talk about this. But this paper is about trying to address the shortcomings in bootstrap ensembles and try to get something that works like a prior. So we call it randomized prior functions. So you add a random network to each member of your ensemble. That provides an offset. We say it's like a prior. And I'm going to visualize it for you in a 1D regression. So I have my data points. That's my training data, 1D regression. And now I'm going to put in a prior function. My prior function is this line in blue. I don't really know anything, they're just wiggly functions. And now I train a 2-layer MLP to counteract this, so that the Q goes through the points. And that's in the dashed line. And the output predictions are in Q. So we can see that by doing this, a powerful network can still go through every point, but the behavior away from the data will be affected by the prior. Now, and we call this a prior function because it's the exact Bayes posterior in linear functions. Now, to highlight that this can do something amazing, I guess we have this domain, a toy domain, an n by n grid with one hot observation. And I realize I've only got 1 minute left, so I've really timed this poorly. But this is one of these classic chain domains where you fall and you can only get a reward if you get the treasure. So there are more than 2 to the n policies, and all of them are 0 or negative reward. But there's one policy that's good. So this isn't just a needle in a haystack, it's a piece of hay in a needle stack. And actually, this algorithm can solve it. Now, I've got a video, I'm not gonna have time to go through it, but please come visit our poster. We've got a blog post, we've got results on Montezuma's revenge, we've got results on that hay in a needle stack problem, and we've even got demo code. So please come by our posters, 155, come say hi. Thank you.
Okay, so our next talk is going to be playing hard exploration games by watching YouTube by Yusuf Aitar. Oh, sorry, this is Tobias Pfaff that's presenting.
Thank you. People are very good at learning from visual demonstrations. We can watch a video like this one and use it to solve a task like this little guy. And this transfer is by no means easy because there's potentially huge gaps in visual appearance, viewing angles, sensing modalities, body differences, etc. But despite that, people are using videos to learn all sorts of skills, like how to knit, to cook, to construct things, to play games. And we want our agents to be able to learn the same way too. And this paper is going some steps towards this direction at the example of learning how to play Atari games by watching YouTube videos. So in this domain, we face several challenges. First of all, the visual appearance might be different between the videos we see and our game environment. There's no actions or rewards available. We only have the video of people playing these games on YouTube. And our key to addressing these challenges is learning an embedding space through self-supervised domain alignment. And this embedding space then is used to construct a robust imitation reward function, which we then use to solve the game using reinforcement learning. So here's how that works. We pick a demonstration sequence out of our training set, which is only like 3 sequences per game, and we pick 2 frames. Now, the self-supervised task is to predict the frame distance between these 2 frames, and we do that in feature space. So first, for each input, we feed the inputs through a deep network and obtain a feature vector. And these 2 feature vectors we then combine and feed it into a very shallow classifier, which classifies the frame distance into several classes. And this effectively trains a feature space which has some sort of notion of temporal continuity, which turns out to be very important to solve this task. Unfortunately, you can't hear this because it's very easy to forget that in Atari we also have sound available. And it's a very useful signal that we should be putting in our algorithms too. And we can do this by adding a second, a cross-model task, which instead of predicting the distance between 2 frames, predicts the distance between 1 video frame and an audio sample in exactly the same way as before. Now, these 2 tasks combined have several interesting properties. First, we show that they can align several sequences which have a domain gap. So here you see 4 different videos. They have more or less the same trajectory. And in the t-SNE embedding on the left, you see they move together when the video moves together. And sometimes you see little things branching off when a jump, for example, is timed differently, which is what you expect to see. If we look at the attention map of our network, we see that it focuses on the player, the enemy, but also things like inventory or items you can pick up. And this is very interesting, because what it means is that we have effectively learned something like a meaningful game state without ever having interacted with the environment. We also see what the impact is of adding a cross-model task on the right. We see that by adding this task, we place more emphasis on events which are associated with a strong salient sound, such as picking up the key in this room. And these are often very important events for the game state, so it's a good idea to include these tasks. So because we now have this feature space which is meaningful in terms of the game state, but is also robust against domain gap and noise, we can use it to guide RL. So what we do is we embed a demonstration sequence in this space, and we reward our agent for loosely following it. And the details are there in the paper. What's important to note here is that because we pre-train our embedding space, this is actually a stable target, and it's easy to learn from. So here's how that looks like. Our agent on the right follows the demonstration sequence on the left, but because it has learned a much tighter control through RL, it is much faster at solving this task or sequence. So the hard exploration games we looked at are very challenging for RL, and also sometimes for humans. The best other method using demonstrations improves on that, but it is outperformed by our method even without any actions available. And our best runs get close to the max score on Private Eye, Pitfall, and mid-level 3 in Montezuma. And if you want to know more, come visit us at our poster, and thanks so much for listening. Thank you.
Okay, so before we begin, just a quick reminder that fire code says we're not supposed to have people standing in the aisles. So if you're standing, and I see a few of you over there, find a seat. There's lots of comfortable seats right up here.
There we go.
How's it look? Yep. Great, so we'll have our next longer oral now by David Ha on recurrent world models facilitate policy evolution.
Oh, hi, everyone. It's my honor today to present our work called Recurrent World Models Facilitate Policy Evolution. It's work done by myself, David Ha, in collaboration with Jürgen Schmidhuber. So this work, at least to me, has been inspired by the literature in the cognitive neuroscience domain. Our mental models, made up of our unique experiences, determines how we interpret the world. They also affect our actions, how we assess opportunities, and also help us solve problems in our everyday lives. In a sense, how we look at the world is through the lens of our mental world models. So in this work, we explore building generative models of game environments. And we also try to train agents to look at their worlds through the lens of their own generative world models. So our generative models consist of pretty basic components. To develop a representation of space, we use a variational autoencoder to compress screenshots of a game into a low-dimensional latent space. To learn a representation of time, we train a recurrent neural network to predict the distribution of future events. Just like how in this network, we train a recurrent neural network to predict future pen strokes of a pen, and we can sample from that distribution to generate different doodles. In our case, rather than modeling pen strokes, we model the distribution of future latent vectors encoded by our VAE, so we can sample trajectories of the future. So in our setup, we have an environment that gives us a pixel image at every time step. We feed this pixel image into a variational autoencoder trained to reconstruct it, and the encoder will output a low-dimensional latent vector Z, our representation of space. We then feed this latent vector Z into a recurrent neural network called M that's trained to predict the distribution of future latent vectors, conditioned or depending on the current information and previous information. And the model M has a hidden state H, and this hidden state of the RNN we're going to use as a representation of time. We'll feed these two low-dimensional representations of Z and H, representing time and space, into a small linear controller C. Now, our controller C can only see Z and H. It cannot see the actual pixel observations. And its job is to output the action A that will affect the environment, causing the environment to generate the actual states for the next time step. And to train our controller C, we want to solve for the parameters of this linear controller such that we maximize the expected cumulative reward of our agent acting in the environment. So to test this simple framework, we tested on a car racing from pixel task from OpenAI Gym, where the agent has to navigate through these randomly generated tracks as fast as possible. So in the procedure, we first collect a data set using dataset rollouts using a random policy. We then train the variational autoencoder V to encode each frame of this dataset into a low-dimensional latent space. So we can then process this dataset into a latent space version of the dataset. We then trained the recurrent neural network M using this dataset to model the distribution of future latent vectors conditioned on the current and previous information. Now, the important thing to note is in this experiment, VMM does not have access to the reward information. Its job is simply to compress space and to predict what's going to happen in the future. So these two networks can actually be trained efficiently using a GPU on a data set in an unsupervised fashion. So while these two models combined have millions of parameters, the controller, in contrast, is a very small model because of the low dimensionality of the inputs, and it has less than 1,000 parameters, which makes this really easy to solve. And in our case, we can even use evolution strategies, in our case CMES, to solve for the parameters of this linear controller such that we maximize the expected cumulative reward of the agents. And here's the citation of the cake that's correctly done. So here's an example of, on the left side, of the actual input frames we feed into our agent. And on the right side are reconstructions using the decoder of the VAE using the latent space. At the beginning, we also train an agent using only Z, not H. So we only give it the spatial information, but not the temporal information as an input. And it still learned to drive, but the policy, the navigational policy, is very non-robust, and it wobbles a lot, tends to miss the sharp corners. But when we then give it also H, so it knows both Z and H, the spatial and temporal information, it learns a more robust policy to navigate, and it's able to seemingly attack these sharp corners by predicting what's happening in the future intuitively. So our model achieved an average score above 900 for this task required to solve the task. And to our knowledge, this is the first solution that's able to solve car racing V0. But that's not the end of the story. This paper has been out for a few months, and people have taken our code or the framework and did interesting things with it. So someone used this framework, but rather than training M, they randomly set the weights of M, and they showed that by using these random temporal features, the score is still okay. So I found that quite interesting. Maybe it's not the weights, but the architecture that makes everything work. Another team, it doesn't mean that DQN is bad or anything. Another team improved DQN, made it 3-layer network with put in dropout and curriculum learning and all this stuff, and they also achieved a score at 900. But the difference here is that in our case, we use a generative model, and our model can predict future frames. So in theory, we can try to replace the environments with an environment generated by M, and we can try to train our controller not using the actual environment by training the controller entirely inside of an environment generated in latent space, so training inside the latent space environments. So to do that, we can take the output of the RNN-M and feed that into a mixture density network layer, an MDN layer, and so that it outputs the probability distribution function of the next time steps of the latent vector in the next time step. We can then sample a next Z, a realization of what's going to happen next, and feed that back in as if it's the actual latent observation. So we can train this controller inside this generated latent space environment, not using the actual environment and not using any pixel information, and we don't require the VAE. So we test this on a simple VisDoom level, where in this level, the agent's unfortunate agent is stuck in a room full of monsters shooting fireballs at it, and its job is simply to survive as long as possible. So the procedure is largely the same as the car racing task, with a key difference of the RNN-M model. In addition to having to predict the probability distribution of the next latent vector, it also has to model the distribution of whether the agent dies or not, and we can sample from that. We need to model this the termination events, because in order to replace the actual gym environments, to get the done events with the generated environment. We then train a controller inside of this generated latent space environments, and then we can deploy these learned policies back to the actual environment to see how well we transfer. So now our model of the environment M is only a model of the actual environment. It's not perfect, and it has flaws. So when we first did this experiment, it didn't really work. What happened was the agent learned to take advantage of these flaws of the model, and went to parts of the environment that was outside of his training distribution. It learned to cheat. So here we noticed that the agent learned to move in a special way, such that the fireballs rarely get shots. And when the fireballs, some of them starting to get formed, the agent can move in another way to extinguish them magically. So of course, this policy is never going to transfer well to the actual environments. But what we notice is in the sampling process, we can increase the temperature. And by increasing the temperature, we can make this generated environment more stochastic and more random. And we notice that a more random environment is more difficult for the agents inside this environment. And it's more difficult for an agent to take advantages of flaws of the environment. Sometimes the agent may just die with no explanation. Tough luck. But in this more random environment, the agent learns a policy that's able to that's more realistic and is able to transfer well back into the actual environments. So in the results, we can see that by increasing the temperature from deterministic to a high temperature, in the virtual score, the second column is the score the agent achieves in the generated environment. By increasing the temperature, the environment becomes more difficult because the score decreases, but the policies learned transfers better when we deploy them in the actual environment. Furthermore, we noticed that when the temperature is too high, it also affects the quality of the policy being learned. For instance, at a temperature of 1.3, the agent learns perhaps a more risk-averse policy with a lower variance of returns at the expense of a lower mean reward. So the method outlined so far has many obvious limitations. It assumes that an initial random policy is enough to collect a data set that maps out most of the space of the environment, which is not true in any environment that requires any meaningful exploration. So even in a simple swing up pendulum environment from pixels like this one, where the initial random policy mainly gathers data when the pole is facing downwards, we notice that the generative model has difficulty predicting what happens when the controller swings the pole upwards because it simply does not have that much data. Although in this case, at the beginning, the controller still learns a policy to try to swing up the pole. It just doesn't know what to do afterwards. So what we can do is incorporate a simple iterative training loop where we deploy these policies back into the actual environment to collect more meaningful data and retrain the world model on this additional data to build a better model to then train the controller. So after 20 iterations, this world model can learn a better generated environments that maps out the states when the pendulum is swung upwards. And when we train a controller on this improved world model, it learns to more correctly how to balance a pole and swing it upwards. So if you're interested in this line of work, there has been some really recent work, maybe out this month, that explores more in depth the concept of this iteratively training a generative model of high quality model of these environments. And they show that by training an agent inside of these generated environments, we can get really good sample efficiencies on domains like Atari or like a continuous control task from pixels. So in the third work, led by my colleague Danny Joy-Hafner, which I'm part of, we actually try to explore more sophisticated forms of these stochastic dynamic models. So unlike this current work, where for simplicity, we train the VAE and the RNN separately, here we try to train the dynamics model end-to-end on the data collected, and we model everything. And also, unlike this current work, where we use a very simple linear controller for simplicity, in this newer work, we also explore things like incorporating a planning module into the controller. And we show that for this control suite task where we learn continuous control tasks from pixels, that we can achieve a pretty good sample efficiency by learning purely from pixels. So this work, in addition to being a paper, it's also available as an interactive web article online at this URL. So if you're interested, you can go on this website to read more about this work and also play around with these interactive web demos. Also, there's code linked if you want to look at reproducing all of the experiments. So this concludes my talk. Thank you for your attention.
How much time do we have? I think we take 3 minutes. So we've got about 3 minutes for questions. So if you have a question, come up to the microphones. I see there's one right there. Go for it.
Okay, thank you for the nice work. My question is, do you have any idea or opinion about training the model with the intrinsic reward? What will be the challenge in that direction and things like that?
So that's a very good question. The idea of an intrinsic reward or curiosity is a natural extension of this. And in fact, Jürgen Schmidhuber has published some work in 1990 where he looks at using the world model to get agents to look at states that is not that aware of. There also are some limitations of these approaches, but feel free to come by our poster later to discuss this further.
Thank you.
Any other questions? Okay, well, let's thank our speaker.
Thank you. Thanks for organizing. We're done. Thanks. Good story.
Okay, and now we have another series of spotlight talks. The first one will be given by Akshay Raj Damija on reducing network agnostophobia.
Hello, everyone. Welcome to my talk on reducing network agnostophobia. Myself, Akshay Raj Damija. This work has been performed at the Vision and Security Technology Lab at the University of Colorado, Colorado Springs, under the guidance of Dr. Manuel Gunther and Dr. Terence Ebold. Agnostophobia means the fear of unknown. This paper is focused towards the response of deep networks to unknown or out-of-distribution samples. Deep networks have widely been applied to a majority of classification problems. Let's see an example using MNIST digits dataset. The aim is to classify the 10 digits on the left. We use the LeanIT++ network architecture that allows us to produce a two-dimensional deep feature representation for the input images. Each dot signifies a unique sample, with the color signifying the digit it belongs to. In order to separate these feature representations, a deep network uses a fully connected layer represented by the 10 decision planes on the right. Now let's consider the response of such a network to non-MNIST or out-of-distribution samples. Here we use the CIFAR samples and pass them through the network trained to only classify the MNIST digits. The black dots representing the CIFAR samples. Another example with the Roman letters. As seen, the knowns and the unknowns are inseparable in the deep feature space and hence also by softmax scores. In 1990, Mutton et al. Introduced an approach for identifying confusion between the known classes. But in this work, we consider it as identifying out-of-distribution or unknown samples. Their network modified the standard softmax by using an additional term to provide a fixed activation to the none of the above class. This activation results in a decision plane parallel to the feature plane such that the center of the feature space has the maximum activation for the none of the above class. This idea of an additional fixed activation subsequently evolved into the background class approach. Here, for every sample, the network learns to provide a different activation for the none of the above class category. The training data for the network includes a small pool of non-MNIST or background samples, which in this case are the Roman letters. In the adjoining figures, we see that the response of Devanagari characters to such a trained network, though the network learns to represent each sample with its custom activation, it fails to represent out-of-distribution samples correctly. This leads us to our approach, which is based on the default response of the deep networks to unknown samples. We find two major observations. First, the magnitude of the deep features of the knowns is generally greater than the unknowns. Second, the entropy of the knowns is generally less than the unknowns. Our approach aims at representing the unknowns at the center of the feature space, while pushing out the knowns to a minimum magnitude of psi. For this purpose, we introduce our two novel loss functions. The first loss, called entropic open-set loss, aims at increasing the entropy gap between the knowns and the unknowns. For knowns, the loss is the same as the cross-entropic loss, while for the unknowns, the loss aims at equal probability for all of the known classes. The second loss, called objective sphere loss, aims at increasing the separation between the knowns and the unknowns in the deep feature space. This loss is used in addition to the entropic open-set loss and aims at making all of the known samples have at least a magnitude of psi, while the unknowns are pushed to 0. For evaluation, we propose a new metric called open-set recognition curve. The curve is produced after sorting all of the test samples according to the maximum probability assigned to any of the known classes. On the x-axis, it has the false positive rate resulting from the unknowns, and on the y-axis is the correct classification rate from the knowns. As seen in the figure, our approach outperforms all of the current approaches. For understanding how this approach may be applied to your work, do stop by our poster number 100. This is the poster on the last corner of the hall. Thank you.
Okay. And our next talk will be on lifelong disentangled representation learning with cross-domain latent homologies by Alessandro Achille.
Thank you. Okay, suppose we have an agent learning in a real-world environment. What's going to happen is that the agent will encounter several different environments which may share factors of variation which are relevant for the task we're going to solve. So the natural question now is, can we learn a compositional representation that can reuse factors of variation we learned in previous environments to solve tasks in novel environments? This entails several things, like understanding when the environment changes, understanding which factors can be reused, and how do we actually learn new factors when we need to do that. But first of all, how do we actually learn factors in one single environment? One technique that emerged recently is to use a minimum description length principle, in particular the constraint capacity increased variational autoencoder training algorithm, which slowly increased the capacity allocated to the representation. This prompts the network to learn, in order of importance, several meaningful semantic factors of variation. Now, the question is, what's going to happen if now suddenly the environment changes? Well, the fact is that factors of variation which are not relevant anymore for the new environment will start acting atypically and destabilize the training process of the network and prompt the network to relearn them, thus forgetting everything we knew about the old environment. However, we can measure when a factor is acting atypically because the marginal distribution of the activations will be very different from the expected prior distribution. If we measure the KL divergence between this distribution, which we call the typicality score, we have a metric both to understand when the environment is changing and to understand which factors are not useful anymore and should be disabled to prevent retraining in the new environment. However, this is only the first part of the story, because after all, if we don't continue training the disabled factors, sooner or later we will still forget about them. But the point here is that we're actually training a variational autoencoder, so we can hallucinate images from old environments in order to still continue training disabled factors that we are not seeing in the current environments, and thus forcing the network not to forget them. When we put everything together in the same algorithm, we obtain a way of training a minimum description length principle for the network, which is able to reconstruct a disentangled compositional representation which meaningfully share semantic factors of variation between different environments. Moreover, when we use this representation to solve a task, this is going to be robust to change of environments and will be able to work on new environment with a reduced amount of training data. And this outperforms the basic variational autoencoder baseline to learn a representation. Moreover, when we learn using this technique, we have several side effects that we observe for our agent. First of all, the agent is going to be able to establish meaningful cross-domain homologies between environments, where the homologies are not based on low-level features of the images, but are rather based on semantic similarities between different environments. And then we also observe the emergence of a categorical perception in the algorithm, meaning that if we observe an ambiguous stimulus, which we cannot understand which class this is going to be part of, the agent is still going to decode the input unambiguously as being of either one class or the other without the extra noise added by the ambiguity, which is similar to what we observe in human perception. And finally, we can also make use of all our past experiences on all the environment in order to inform us of what is a possible policy for exploration based on imagination of states which we believe are possible based on what is possible in past environment, which further improves both exploration and data efficiency of the novel, allowing also zero-shot learning for new environments. And so for more details about this technique of training compositional semantic representation, please come to our poster. And thank you.
Okay, so our next talk is going to be geometrically coupled Monte Carlo sampling. And Krzysztof Choromanski is presenting.
The most complicated Polish name to pronounce. Good afternoon. It's a great pleasure to give this talk here. So what we focus on in this paper is basically a new method for doing Monte Carlo sampling that outperforms the standard baseline, gives much more accurate estimators with lower variance. We call this method geometrically coupled Monte Carlo sampling, or GCMC. And we focus here on the setting where the problems are high dimensional, and we would like the number of samples to be substantially smaller than the dimensionality of the problem. The video of the Miniature robot presented here is obtained by applying the GCMC method to estimate the gradient of the Gaussian smoothing of the black box RL function in ES-type algorithms for policy learning. I will talk about it in more detail in a couple of minutes. So from the mathematical point of view, what we want to do is to estimate expectations of functions of certain random variables by finding optimal joint distributions of samples. And we prove in the paper that those optimal joint distributions can be obtained by solving multi-marginal transport problem, often analytically tractable. Now, there are lots of applications of the method, but basically whenever you use Monte Carlo methods, you can apply it whenever you are interested in estimating quantities of the following form. Variational autoencoders might be like one example where you would like to estimate the gradients of the loss functions. Those gradients are given as expectations of certain variables involving isotropic distributions, Gaussian distributions. Since I'm in the robotics team, I will talk a little bit more about robotics applications, policy learning. So the standard way of doing this estimation would be to use standard, so let's say antithetic-based Monte Carlo sampling. In this setting, different antithetic pairs are chosen independently, and furthermore, within the pair, the lengths of vectors are exactly the same. Now we break this rule in GCMC. The directions are orthogonal, so they are coupled, they are correlated, and also the lengths are correlated in a very particular way. And that gives us the reduction of the variance and better concentration results in general. So to talk in more detail about robotics applications, we want to optimize the policy, which is a mapping from state to action. It can be encoded by the neural network. And that approach leads us to the black box RL function that takes as an input the parameters of the policy, let's say the parameters of the neural network, and outputs the total reward obtained by an agent applying this policy in the particular environment. In that setting, the function doesn't need to be differentiable, so there are different ways of making it differentiable, different smoothings, like a Gaussian smoothing. And now the gradients of those smoothings can be described in terms of expectations. This is where Monte Carlo methods can be applied. So the standard way of estimating the gradient would be to use either finite difference method or more recently unstructured independent Gaussian directions. What we basically try to do here, and we show that we can successfully apply here, is to use those new Monte Carlo sampling methods to get more accurate estimation of the gradient. On the top of that, we can use standard gradient-based techniques to learn good quality policies in ES-type setting, evolution strategy, policy optimization. So how does it work? Like if we take the standard antithetic pair estimator that was recently very successfully applied by Salmans et al. From OpenAI to show that ES strategies are really work well for policy learning, then we would actually get something that we call antithetic inverse length coupling estimator. And in that setting, the lengths are coupled in a very particular way. And this is how exactly they are coupled. It's green box. F-chi stands here for the CDF of the chi distribution. So they're no longer the same length. Now, how it works in practice, these are some videos of the simulator Miniature robot walking. All those policies are linear, 96 dimensions or 96-dimensional gradient vector learned with GCMC. And capital N stands for the number of samples that we use per iteration. So we see that with GCMC, we can reduce the number of samples substantially and still get good quality behavior. And that's pretty much it. If you want to know more details, room number 210, poster number 97, and we'll be very happy to answer more detailed questions. Thank you so much.
Okay, so our next talk will be on scalable Laplacian K-modes, presented by Imtiaz Masood Zico.
Hello, everyone. I am Zico from ATS Montreal, and I will talk about a scalable Laplacian K-modes. So we advocate Laplacian K-modes for joint clustering and density mode estimation. The first term is the K-modes term, which provides the modes of each cluster, as in popular mean shift. The second term is the well-known Laplacian regularizer, which enforces that the nearby data points should have similar assignments. And this is well cited for spectral clustering and semi-supervised learning. The task is to minimize this combined energy over the discrete assignment variable z, subject to the simplex and integer constraint. So while Laplacian K-modes, first, it can handle the non-convex clusters easily, as in spectral clustering. Secondly, unlike means, it provides modes as prototypes from valid input set, and this can be useful for high-dimensional manifold structured inputs, such as images, where the simple means may not be the good representatives. For instance, here there are several semantic classes like building and highways, and from our clustering results, we get the mode images, which conveys the most frequent semantic information of each cluster, where you can see the means are not that good representatives. So minimizing Laplacian K-mode is very challenging due to the simplex and integer constraint, and also for the Laplacian term itself, optimizing which is NP-herd. The well-known spectral relaxation can be used. However, it has the high computational and memory load when n is very large, and making it scalable is an active research. So if we relax the integer constraint, we get the convex relaxation, but it needs to solve jointly over the number of data points and the number of clusters. And also, it has an additional overhead of projection, simplex projection, and all this do not make it applicable for larger scale clustering. So our main contribution is to provide a concave relaxation of the Laplacian, which enables a parallel structured algorithm, and it averts the simplex projection step. So we can write the Laplacian term in these two forms, which are equal at the vertices of the simplex, but they are different when the ZP is in the relaxed domain. And note that we do not relax the variables in this term, which make our relaxation tighter to the original Laplacian objectives. So we take this term, we discard the constant, and this is a concave function. Thus, optimizing the first order approximation at each iteration decreases the original function with guaranteed convergence. And this concave relaxation can be used for Laplacian in any other context. The K-modes term can also be bounded like this, and we introduce a convex entropy term which averts the simplex projection step. So this is the bound for our relaxation, and we can see this is sum of independent function. Thus, we minimize it independently of each data point with guaranteed convergence, and thus make it scalable, and it is a parallel structured algorithm. And this is convex and affine, so we get the closed form solution for the Z updates. We also show that we can get the modes from this proximal optimization, and interestingly, this is already inside our Z updates, but with a soft approximation of the hard-max operator. But this is linear in n, and unlike mean shift, for mode estimation, we do not record the gradient descent. It is independent of feature dimensions, and it can be used with arbitrary kernels. So these are some of the results on image clustering, and we get competitive performances in terms of speed and accuracy in different data sets having different features. And note that in some large-scale data sets, the spectral relaxation and the convex relaxation do not scale up. And we also get better timing than k-means in high-dimensional feature space. And this graph is showing that we consistently get lower values for our original discrete Laplacian objectives. And this indicates that our Laplacian relaxation is much tighter than a direct convex relaxation. And this is how we make scalable Laplacian K-modes. So if you have more questions, you can come to the poster session and we can have more discussion. Thank you so much.
Okay, so I believe that's the end of the session. Let's thank all the speakers just one last time.